The first test you try is the divergence test.
Right.
And the reason you try it is because if it does not go to 0, like if it goes to 1 or anything like that, then it diverges. But if it does go to 0, then you gotta go back and try something else. Okay.
Okay.
And that's critical, because you'll get problems like, let me see if I can find one here.
And this is we went over geometric series and then harmonic series.
Well, this is just in general, like this
Okay.
is when you get to the end of this chapter, you're gonna say, I wish I had known this now, because if you know it's a geometric, you start with a geometric test or a harmonic or
it
whatever.
Converges to A/1 minus R. That's what we use.
Yes.
When R
Okay.
is less than 1.
Right.
Okay.
But what I'm trying to show you here, let me just start with 14.
Okay.
Because this one does not converge. You truly do want to start with the divergence test. So the limit as k goes to infinity, k plus 2, k plus 3 squared. So there's a lot of kind of words that, and maybe some math that go along with this, but you have to, I'm gonna expand this so you can see it. The bottom is k squared plus 6k plus 9. So as you go to infinity, everything except the power term or the leading term, like these don't matter. This is what matters right here. And the limit what is meant by the divergence test is the limit in this case is k goes to infinity, a sub n or a sub k in this case. If it does not equal 0, you can say that it diverges. And that's what's going on here. This one goes to 1 because it's 1k squared over 1k squared. And this doesn't go to 0, so it diverges. Right. And you're done. Like, you don't have to go any further than that. And like in a typical quiz test thing, you'll get a problem like that. And sometimes it's disguised like a geometric series. Is this okay though? Like you saw this in class, hopefully. Okay. Yeah. So let's say I give you one, and I'll get back to your problems in a moment. I'm going to use n instead of k. So let's say it's n equals 1 to infinity, 4/3 to the power of n. This is geometric. Right. Okay, and this is your a sub n. Your a sub n is 4/3. And the limit as n goes to infinity, 4/3 n, well, it does not go to 0. Okay, and you might be thinking, well, what does it go to? Well, let's look at it. It's 4 to the n over 3 to the n. So do you see how the top is growing faster than the bottom? So we know that it does not go to 0. Okay. But if it were switched, if it was 3/4, then it would. Right. And it's geometric. So you could sit there and say, oh, it's a1 over 1 minus r. But that would be wrong because it doesn't converge in this case. So it has to, oh, right, okay, yeah. That's why this divergence test is so important. Like, first be like, all right, does it even go to 0?
So you can use the divergence test for geometric series as well?
Yes, because not all geometric series converge. Geometric just means they have a common ratio between terms. Okay. And the common ratio could be bigger than 1. Okay. Alrighty. Okay, so let's go to some problems that actually do converge, starting with 13, if that's okay.
So that one diverges as well?
Yes.
Okay.
Yes. So we'll try to limit our discussion now to things that actually converge, because you know, I don't want you to live in this world of thinking, no, nothing converges. Like, textbook problems do. There's a lot of rewriting that you end up doing, and you're using a lot of exponent rules. Okay, so this one right here, it's 3 to the n over e to the n times e to the minus 1. And that's just your exponent rules. Okay, So this e to the -1 is really, it really goes up top. It's really e. It's really e, and then it's 3 to the n over e to the n, and then you combine these, so it's 3 over e to the n, and then this e you can bring out, the constants you can bring out, just like with integrals. Okay, so in this case, r is 3 over e. Is 3 over e absolute value? Because there could be a problem where there's a negative. Is it less than 1? And you got to remember that e is approximately 2.7 something. So is 3 over 2.7 something, is it less than 1?
No.
No. So actually I lied. This one does not converge. All we'd have to do though is switch the order here, and it would.
Okay.
All right. So, geez, that one didn't work out very well. All right. What to do next? Let's do 17 next. We'll come back to
Alright.
15.
So could you use the divergence test for any, like just,
Series, yes.
yeah, okay.
Yes. We should have done that actually, because we would have figured out that this e grows faster than 3 to the n.
So is that what you would recommend doing before? even
Oh,
trying this test?
it's yes, but it applies more to like a problem like 14, which is a polynomial over polynomial. It doesn't really apply to these ones that are numbers to powers.
Okay,
It doesn't work as well, but it can. So like here, okay, so your an here is 1 plus 2 over n to 3 over n. So the limit as n goes to infinity, a sub n, when it gets large, this 1 is irrelevant. So it's 2 to the n over 3 to the n, which the 2 is less than 3.
that'll
So
be going to 0.
it does go to 0 now. So this is where I'm not sure what to tell you, because I can't remember what I had to write when I took this class or classes like this. Like I would just write 0 now, but do you know if you need to put any words here to do that?
Like saying whether it converges or diverges?
Well, no, just can you just write 0, or do you have to like show work, I guess?
Well, like you did, yeah, you have to show work. I don't think you have to put words.
Okay, so like for example, you could divide both the top and the bottom by like 3 to the n, and then you would show that this thing goes to 0. But like that, when I say show work, I'm
Yeah, I
asking.
could like circle the 2 to the n over 3 to the n, circle it, and then like fill in infinities for it,
Okay,
for the ends, and then
yeah,
show that it goes to 0 or
okay,
equals 0, I mean.
all right. So this tells us, and this is the wording, is the divergence test is inconclusive. And the reason is because it goes to 0. So it may still diverge, but not by this test.
Okay,
And that's one of the things I think is unclear, is like, if it does not go to 0, then it diverges. But if it goes to 0, it could still diverge.
interesting.
Yeah. And the most common example of that you've probably seen is sigma 1 over n. This goes to 0, but this thing diverges.
I think I have.
Yeah.
I think we did something like that.
So that's the mistake, to think, oh, it must converge. It may or may not. Remember we were doing horn, what was it, Gabriel's horn last week? You're into that space now where it's like, yeah, its volume is known, but surface area is unknown. It goes to 0, but it doesn't converge.
Yeah.
These things that seem to be paradoxical, if you will. Okay, so there's a rewrite that's needed here. You want to divide both of these terms by 3 to the n. So on the left here, it becomes 1 over 3 to the n. The reason you can do that is 1 to the n is always 1. So you can go this direction and write 1 to the n up top. plus, and then this is a good idea for, early first time student here is to actually make two sums here. And this is 2/3 to the n. Okay. So this is where again, I'm not really sure what to tell you to do for work. These are both geometric.
Right.
The first one has an r equal to 1/3, and the second one has an r equal to 2/3. So their sum, the sum of an infinite geometric is a1 over 1 minus r. A1 more generally means, or sometimes it's A0, it means the first term. So if n is 1, you have to put 1 into this to get your first term. So that's A1 there. And then it's 1 minus 1/3 there. If it started at like 6, you would put n equals 6 in for your first term. On the right here, your first term, we put n equals 1, it's 2/3, and then over 1 minus the ratio, which is 2/3.
So because the divergence test didn't work, you had to use the
divergence test only told us that it did not diverge.
right. And when that does, like when that happens, that's when you go to the this
You go to another test.
rules. Okay.
And so like right now, geometric.
Yeah.
I think you mentioned some sort of harmonic, but there's other ones. There's the integral test, the
Yeah, we
ratio
learned the integral
test,
test.
the root test, comparison test, and so on. There's a few. I mean, I think that's all of them, but like
Yeah.
you have to decide. And
We're
that's
not doing the integral test. Won't be on. It'll be on next week's quiz.
yeah. So since it converges and since it's geometric, you can actually figure this out. So it's 1/3 over 2/3 plus 2/3 over 1/3. So this becomes 1/2 plus 2 over 1, which becomes 5/2, I guess.
And that's converges, right?
Yes. So that's another part of this is it could be that it converges, but you don't know the value, unknown value. Or it could be that converges and you know the value. So like just because it converges doesn't mean you can say what it converges to.
When would be the case for each? Like
Nothing you've seen so far. For the
I think we have.
The comparison test is when this first occurs, because all of these in this problem set say if it converges, find the sum.
Okay, let me see. Integral test. Actually, wait, never mind. Just kidding. All right, I'm good.
Okay, so let's look at, we do have to look at a few that do not converge. I didn't realize there's so many here. So let's look at 15. So you start by doing the divergence test. Okay, so your an is n minus 1 over 3n minus 1, and the limit as n goes to infinity a sub n, which is the limit as n goes to infinity n minus 1 over 3n minus 1. Do you see that this goes to 1/3?
Yes.
Because it's like, yeah, great. So this does not equal 0, which means it diverges.
Right.
And you're done. This is the best possible outcome for like doing this problems. Okay. Because if it did go to 0, you still don't know whether it diverges or converges and you got to do something else. You just wasted an iteration step.
Okay.
So let's look at 18. Is that okay? Like hopefully, like this is the work I would expect to see. I actually wish this part of the course was like more of an oral test, because it'd be better to have a conversation with a student and say, okay, why are you doing this? And what are you thinking? So here your AN is cosine 1 over n. And the limit as n goes to infinity a sub n equals the limit as n goes to infinity cosine 1 over n. And then if your instructor is really big on this, you could actually move this inside here. You can say the limit as n goes to infinity 1 over n.
Mhm.
So what does 1 over n go to as n goes to infinity?
0.
So this becomes the cosine of 0, which equals 1. And that does not equal 0. So this diverges.
All right.
'21 we'll do next. Okay. So your a sub n this time is arctangent of n. And the limit as n goes to infinity, a sub n is the limit as n goes to infinity, arctangent of n. Do you remember what the graph of tangent or arctangent looks like? Do you remember either of those?
Tangent? No.
So there's a few of these.
I think I remember what you did.
Yeah, there's a few of these that you definitely want to remember. So tangent looks like this. It's the S. And then arctangent is the inverse. So you end up actually revolving it over this line right here.
Oh, okay.
Okay. And it has an upper and a lower bound, which is pi over 2.
Okay.
So the limit of this, and if you don't know the graph, you would have no idea. But the answer is it's pi over 2. And so there's no work. Like you could just write that down. They wouldn't know where it came from. But this does not equal 0.
Right.
So this diverges. And this is why it's so important to do the divergence test first.
Right.
All right, so let's look at.
Can we do some like 20? Can we do 23 and 24?
Yes, I was gonna do. Yeah, I was gonna do some. Oh, okay, yeah, 23 and 24. Good. So here, let's see here. Yeah. Okay. All right. So I would probably tell you to write a formula for this, but let's just look at kind of the pattern here. The top is always 1, okay, and the bottom is getting bigger. It looks like the bottom is going up by 3 each time.
Right.
All right. So in that case, eventually this is 1 over infinity. Would you agree with that?
Yeah.
So, but to be like fully complete here, you really need to write a formula, because we can see that the limit as this goes to infinity is 0, but we need a formula. So it's 1 over, and then because it's going up by 3 each time, you might want to put like n equals 1, n equals 2, and so on until you kind of figure out a pattern here. But I would just say that is probably reasonable.
Okay.
So the limit as n goes to infinity, a sub n equals the limit as n goes to infinity 1 over 3n. This equals 0. Okay, all this means, and I'll also write in words here, does not diverge.
Right.
According to this test. Might diverge from something else.
Okay.
Okay.
So that's just the
now,
answer. It does not diverge.
For the moment, we're going to do more.
Okay.
So we have the sigma n equals 1 to infinity, 1 over 3, 1 over 3n, like that. So here's what I'm going to do. I'm going to rewrite it n equals 1 to infinity, 1/3 times 1 over n. Is that okay? I wrote that.
Yep.
You can bring the 1/3 out. Okay. This right here is known to diverge.
Right.
So a number times a diverge still diverges. So you would say something like, since sigma n equals 1 to infinity, 1 over n diverges, so does constant times sigma n equals 1 to infinity, 1 over n. Something like that.
Okay.
You want to somehow use what is this, like logic? Maybe you did you ever do like truth tables in maybe a previous class or previous?
It's not ringing a bell.
Okay. But so there's these things where if you say if then, and that's what's kind of going on here. It's like, okay, since this is true, then this follows. Is that okay?
Yep.
All right, let's look at 24. All right, so when you look at 24, what do you notice is happening in the top?
It's alternating.
Alternating between 1 and 2, but the bottom is getting really big.
Right.
So it doesn't really matter what it is down here. It doesn't matter whether it's 1 or 2. It's gonna be over a huge number.
Right.
So it probably goes to 0, probably. But it like that's kind of how you got to think about it. It's okay, it looks like it goes to 0. You still need to come up with an AN.
Wouldn't the top be -1 to the n minus 1? Wait. Would it go to the n minus 1? Would that be the exponent?
So it's like I don't want to make this too complicated, but like you need the middle number between them, which is 3 halves, and then you're either adding a half or you're subtracting a half.
Okay.
So it's like, and I think I'm overcomplicating this, and that's part of the problem with these problems is if you don't get the right sequence or you make it too complicated, it doesn't work.
Right.
But it's the top is 3 halves plus -1 to the power of n times 1/2.
Okay.
And you can see when n is 1 that it works, and you should really, you should always test these to see if they do.
Right.
Do that. You also, I actually I do see that I made this way too complicated. You actually have 2 going on here. Like, let's not do it. Let's scrap this. It's really 1/3 plus 1 over 27 plus 1 over 243. And then your second one is 2/9 plus 2 over 81 plus 2 over 729. And let's find the sum of each of these individually.
All right.
Is that okay?
Yep.
All right. So the first one is 1 over 3 to the, let's see, that's 1, that's 3. So it's going up by, that's 5. So it's going up by 2 each time. So is that 2n minus 1, something like that? I think that works. So when n is 1, so okay, that's kind of another thing I have to say. So to go even and odd, even is 2n plus, no, sorry, 1, 3, 5, 2n minus 1, and then even is 2n, but odd could also be 2n plus 1, depending on where you start your
What would be
in indexing.
What would be where you start from if you got 2n plus 1?
0.
Oh, okay.
So this is n equals 1 to infinity. And that's, so you do that later in this course. I think if you re-index from 0, it becomes 1 over 3 to the 2n plus 1.
Okay.
But you really want matching indices here. So this one on the bottom here, it's always 2 on the top. And then like I see this as 9 to the 1, 9 to the squared, 9
right
cubed. And this I should have wrote this 3, 1, 3 cubed, 3 to the 5th. So now it's just 9 to the n.
A lot simpler.
A lot simpler. And I don't know how to tell you to like, yeah, like just do a lot of the problems. It's not that easy. It's
Right.
you've got to be able to see things when you do it. So let's break these apart because you're really adding them together. So the first one, if I do a small rewrite here, actually, do you see the common ratio here? That's kind of another way to do this.
What do you mean?
So like there's a bunch of stuff we could do here, but the common ratio, R is always like the next term over the previous term. So for example, it's 1 over 27 over 1 over 3.
Okay.
So it's this second term over this one,
Mhm.
and that should equal this one over this one.
Uh-huh.
And so to get this, that's gonna be a little easier than manipulating this.
I think that's how she did it. Maybe. Let's see.
I think it's 1/9.
Hang on.
And you know, this is all for the first one here. We're gonna do the same thing for the second. So if you get that, your sum is A1 over 1 minus R. Your A1 you already have, it's the 1/3. It's just going up and figuring out which one was first, 1/3 over 1 minus 1/9.
Could you scroll back up for a second?
Of course. How far?
Go all the way up to like where you pasted the problem.
Okay.
So would doing 2/9 over 1/3, would that do anything?
No.
Okay.
Well, I don't know. Let me look. Let me go down here and write it. I didn't think of that. So let me look. 2/9 over 1/3. Okay, this would equal, you multiply by the reciprocal, it equals 2/3. Okay, and then 1 over, I'm sorry, 2 over, well, no, I actually need to do the next one. 1 over 27 over 2/9. So if I do that, I'm multiplying top and bottom by 9/2. That becomes 1/6. Let me make sure I got that right. Yeah, I do. So the 9 up here, you know, cancels that, it gets 3. So this becomes 1/6. So that's why I think you've got to do the 2 separate series.
Okay. All right, that's fine. I was just looking at an example in the notes and maybe trying to do that, how we did that one.
If they're all the common ratio, that's great. Like the most I've ever seen is 2 sums like this, but it could be 3. I mean, you could have every
Right.
fourth term be the one. So you get your sum of the first one. The second one is the same deal. The common ratio would be the 2 over 81 over 2 over 9, which is 1/9.
Mhm.
Okay, so then your sum is the first term. Your first term is 2 over 9, 1 minus 1/9. Then you get those two numbers and add them up together.
Okay. Alrighty. Those were a little much,
Yes.
or that one at least.
Yeah. We should look at 22, if that's
All right.
okay, unless you got, because this one's somewhat deceptive. All right, so what is the very first thing we always try?
Divergence test.
Divergence test. So the limit as k goes to infinity, and some instructors are big on like, you have to use the k. I like n, but like if it's problems in k, you should use k.
Right.
A sub k equals the limit k goes to infinity, cosine 1 to the power of k. Well, I'm not sure. So any idea what the cosine of 1 is as a decimal approximation?
I don't.
You don't. I don't either, but I just plugged in my calculator and this does matter. Let's just say you somehow knew that this was 0.54 to the power of k. Okay. Now, if k is 1, 0.54 to the power of 1 is whatever that is. If k is 2, it's 0.54 to the power of 2. Did it get smaller or bigger when you square a number less than 1?
Smaller.
Smaller. So it gets smaller and smaller and smaller.
Right.
And this does actually go to 0.
Okay.
Okay. So all that tells you is it does not diverge. Maybe it converges, maybe it doesn't, but we don't know yet. So we have to do more. So here's the next thing to do. If you're totally unsure what to do, is you actually do start plugging in values. So it's cosine of 1. When k equals 2, it's cosine of 1 squared. When k equals 3, it's cosine cubed of 1, and so on. What is the pattern here? What is it going up by each time?
1.
Cosine of 1.
Oh yeah, cosine 1, right?
So believe it or not, this is geometric, and r equals cosine squared of 1 over cosine of 1, which is cosine of 1. So this is the r value, even though it's not a nice number. It is, but it works. Like this is your r, and this is less than 1.
Right.
So this is geometric with r equals cosine of 1. So even though you can't get like a nice number, you can still figure out the sum is a1, the first term, over 1 minus r. Your first term is cosine 1 over 1 minus cosine of 1. That's the kind of question your instructor from last semester would probably give you.
Probably.
But the point is it can look bad, but if it's true, if the cosine is less than 1, then, or if the r is less than 1, then it converges. So I guess another small little thing here is, as I have not done a good job of like saying like it converges. We've been dialoguing about it, but your instructor is going to want to see that word.
Right.
Or C. I don't know.
No, yeah, you just write a converge.
Okay. Okay.
And that's when it's less than 1.
Yes.
When it's greater than 1.
It diverges.
Right. Okay.
So I love these sort of like forks. So if you get to if you think it's geometric, okay, if the absolute value of r is less than 1, it always converges.
Right.
If the absolute value of r is greater than 1, or greater than or equal to 1, it diverges. And that's like if you go down the geometric path, right? Because we started out. Yeah, go ahead.
Oh yeah, when we have geometric series, that's the rules that we just go with. Like we always do the R thing.
Yes. And this is what the instructor's looking for. They want to see like absolute value of r less than 1, but they more specifically want to know what your r is. They want to be like, oh, cosine of 1 is less than 1, so it converges. That's what they want to see, I think.
Yeah.
All right, so the only problem we have not done is 19 and 20.
All right. Let me look at those.
Is there other stuff though you want to cover tonight?
No, that was pretty much it. Do you think we should do one like 20? I don't think we haven't even seen anything like 19.
No, yeah, 19 is not a good question for you guys. It's actually a root test, and I believe it diverges because the sum of 2 does not converge. So 20 is, the 20 is geometric. They're two geometric ones. 20 is, I would expect you to get like either the first part or the second part, not necessarily them together,
Uh-huh.
but it's geometric. They both converge because the ratio is less than 1.
All right.
I would just comment here, like again, I don't think you're gonna have this, but like pi over e to the n. Okay,
Uh-huh.
this diverges because pi is approximately 3.14 and e is approximately 2.7. But if you go the other way, this converges.
0.
Yeah, you might want to just remind yourself of some of those values. Arctangent was a good one that we did, the 21. The arctangent, because it does actually approach a horizontal asymptote, you know, it approaches pi over 2 like that, going the other way, minus pi over 2.
Yeah, we could be done now. That's all I really wanted to go over.
Great. You know, if you understood this, if you got some time, maybe work them out again, but whatever you're doing is probably working. So
Alrighty.
cool. Thanks so much, Trent, for scheduling. I'll send you notes here shortly and I'll see you next time.
All right, thank you.
Have a great night. Bye now.